It's a few minutes after, so let's go ahead and get started. My name is John Neeson. I'm a sales engineer here at Dorse, and I'm joined by Chris and Scott, also sales engineers who could be helping you guys out. Today's presentation is about laboratory and fume exhaust systems, as you can see there on the screen. And we're very lucky and fortunate to have Greenheck's absolute best lab and fume exhaust engineer with us, Justin Zahn. Like Chris and Justin were just talking about, if you have questions, put them in the chat and we'll get to them. I'm thinking since we'll have a little bit smaller of a group here today, this could be more of a an open format kind of thing. So if you've got any questions at all, just don't be afraid to put them in the chat there, and we can probably get them addressed and get them brought up with Justin. So having said that, Justin, why don't you go ahead and get started for us?
Awesome. That sounds great. Well, hello, everyone. Again, my name is Justin Zahn. I'm an application engineer here at Greenheck. My main job is to work on our laboratory and fume exhaust line. Doing these presentations, helping with some field issues. I also do a little bit with our ductless garage transfer fans. I also work a little bit on our data center side as well. Today, we're going to be going over some of the basic system guidelines when it comes to laboratory exhaust, basics of operation. Then we'll start diving into the products, the nuts and bolts of these products. And then after that, towards the wrap up, I actually have another demo I'm going to dive into called our virtual lab. It's a little bit more interactive, a little bit better than a PowerPoint, and hopefully, lets people ask a little bit more questions as we start going through the systems in live time. So what are the main objectives of a laboratory exhaust system? We want to remove any effluents or contaminants from that space below the fan and expel them above the roof line into the atmosphere, and without any re-entrainment into building makeup air systems. Okay, so that is, that's the whole goal of these systems. Usually, whatever these systems are exhausting is extremely hazardous to, the general public or people, on the roof deck working on these fans, and sometimes even deadly. Okay, so we want to make sure that we are, getting that effluent or contaminant far and above that roof deck level, to a safe point where, it can dilute itself before coming back down and coming in contact with that general public. So how do we design our laboratory exhaust fans? Okay, we follow two key standards in the industry. The first standard is going to be ANSI Z9.5, which states the discharge velocity. So the air coming out the top of these fans needs to be moving at a minimum of 3,000 feet per minute. Okay. Again, that kind of comes back to, we don't want any possibility of re-entrainment back into makeup air systems or having this air coming back down into the general public too soon. And having this 3,000 feet per minute minimum allows us, to stay on that safe side. Okay. Generally, when it comes to these laboratory exhaust systems, you'll see 4,000 feet per minute, 4,500 feet per minute or whatever. Most of the time it is a decent amount higher than 3,000 feet per minute, but 3,000 feet per minute is usually, the industry standard on this. And again, just because we know it's safe, we know it works, anything below 3,000 feet per minute, that's when, once you start lowering your outlet velocity, that has a direct effect on your plume height. So the lower the velocity, the lower the plume height, which creates that possibility of, possible re-entrainment, back into those makeup air systems, or, the possibility of this exhaust coming down a little bit too soon and, being introduced back into the general public. So expanding on ANSI Z9.5, ANSI Z9.5, again, has been the standard for the longest time, but this standard now is actually changed in the industry. Now it is up to you or whoever's in charge of that lab space to determine what kind of outlet velocity you truly need coming out of these fans. Again, most manufacturers are still going to recommend 3,000 feet per minute, but if you can get away with a little bit lower velocity, why would you not do that, right? These fans, as everybody knows, are energy hogs. They take a lot of energy to run. So, if you can go at 2,500 feet per minute or 2,000 feet per minute, everyone wants to jump on that if possible, okay? Because you're saving energy and still being able to maintain, your targeted plume height. Moving on, the next standard we follow in the industry is going to be NFPA 45. Okay, so that states that these fans have to be 10 feet tall minimal from the roof deck up. You're going to see one of our actually employees standing on the roof here next to a couple of our Vektor H's. And these fans are obviously well above his height. They look actually a little bit taller than 10 feet tall. The reason why we need to have, a 10-foot tall minimal is because we don't want someone walking up on that roof, and having the ability to stick their hand, their face, or whatever other body part over these fans, okay? Because as we talked about before, generally whatever these fans are exhausting is usually pretty hazardous to the general public and sometimes even deadly. So having these fans at 10 feet tall kind of eliminates the possibility of any worker on that roof coming in contact with that exhaust. A common question we get a lot in this industry is, can you make your fans 8.5 feet tall, 9 feet tall, whatever it may be? The answer is always going to be no. We always want to stick to that 10-foot tall minimal. And again, that's our standard. Most of the time, these systems are much taller than that, but that is usually what we like to stick to. So, moving on, talking about ANSI Z9.5 a little bit more and talking about how that standard has changed now in the industry. One way around, avoiding that 3,000 feet per minute, if you want to, and if you don't want to take the manufacturer's recommendation, is through a wind-wake analysis. For those of you who don't know what that is, the wind-wake analysis is basically they take a mini 3D printed model fan and they place it, let's say, these fans are going into downtown Seattle, okay? With that, with that, they would take that 3D printed model fan and then they would create that 3D printed model layout, let's say of downtown Seattle. They would place that fan within that layout. And then from there, they would place this whole thing into a wind tunnel. In that wind tunnel, they would then rotate this whole layout. As they are rotating the layout, they are blowing some kind of colorful smoke up that 3D printed model fan and studying the effects of different wind speeds. I should say the effects different wind speeds has on the plume height. Okay. It sounds pretty complicated, and that's because it is. It's a great tool that's at everyone's disposal if you don't want to take the manufacturer's recommendation. What I will say, though, for the people that are aware that ANSI Z9.5 has changed, we tell them that they are more than welcome to go get a wind-wake analysis if we get any pushback on that 3,000 feet per minute. They go get a price for the wind-wake analysis, and once they see the price, they usually come back to Greenheck and they say, okay, we'll stick with 3,000 feet per minute. So it's a very accurate, tool at your disposal for sure, but it's definitely very, very expensive. Okay, and for larger jobs, there has been people that have utilized this, but for most jobs, a lot of people will just stick with that 3,000 feet per minute. All right, so moving on now, everyone on this call, as I'm assuming, has heard of AMCA before. Why I'm showing you this slide is because there are still some laboratory exhaust fans out there in the industry that are not AMCA certified. So AMCA, third-party testing service, basically solidifies that all the data we are giving you is 100% true. And again, these are life safety applications, so you want to make sure you're being as accurate as humanly possible. Being AMCA certified is a way to solidify that. But there are two different ways to say you're AMCA certified. One is incorrect and one is correct. The incorrect way is to say you are tested in accordance with AMCA standard 210 or 260. Okay. And that is, again, that's usually all sometimes competitors will say, and customers will sometimes go blind. They hear AMCA, they hear they're tested in accordance with AMCA, and they think that that means they are AMCA certified. That is not the case always. What you want to hear is that you are licensed to bear the AMCA certified ratings seal. So you're licensed to have that sticker on your fan. And my job is to spread this knowledge throughout the industry to make people aware of it, because obviously, these fans, they are extremely expensive systems. That's how they are. That's how they're built. So you want to make sure that, all the data that is being provided to you, you want to make sure that these fans are going to perform the way we say they're going to perform. Okay. And being AMCA certified is a great way to solidify that. So moving on now, we're going to talk about, some of the best practices as far as, stack design goes. So we want to stick with straight stacks with conical nozzles. Okay. So straight stacks, nothing on top of these nozzles. That's the best route to go when designing these systems. We want to, make sure that there's no negative effects on our plume height coming out of these nozzles. So again, straight stacks, nothing on top that could potentially affect that plume height is the best way to go. The worst way to go, we'll move to the bottom of the screen here, is you're going to notice this gooseneck here on the side. All I can say is please don't do that. We run into some pretty I'll say unique situations when it comes to the laboratory exhaust world. We see a lot of different questions come in. One thing we always recommend is please do not add a gooseneck type stack on to these laboratory fans, just because it completely defeats the purpose of these fans. You're not creating any kind of plume height. Whatever you are exhausting is completely being dumped back onto the roof. Okay, so that makes it dangerous for the people on the roof. And on top of that as well, depending on where these stacks are, let's say you're dumping it right over a building, that makes it hazardous to the general public below. Okay, so stick with these straight stacks, avoid the gooseneck. When I first started at Greenheck, I actually went up onto a roof with my boss, and I knew very little about these systems at the time. Okay, we walked up to this system, it was gated off. And I didn't notice it at first, but there was a gooseneck stack on top of this fan. And needless to say, my boss, he grabbed me and he said, we're going to get the heck out of here, just because we had no idea what was being exhausted on that roof. We had no idea how hazardous it was. And again, whatever was coming out of that particular system was completely being dumped back onto the roof. Okay, so it just completely defeated the purpose of the laboratory exhaust system. And again, if that is a stack that you are wanting to use, then we would recommend, moving away from the laboratory exhaust products. Okay, because there's no point of having a laboratory fan with a gooseneck type stack on it. All right, so moving on now. So we talked a little bit about ANSI and the outlet velocity, 3,000 feet per minute, and how that has a direct effect on your plume height. Well, there are two different ways to calculate plume height in the industry. The first way is through the modified Briggs equation. Fairly simple. This equation is now more or less being pushed out of the industry, not being used too much anymore. Nowadays, the industry is moving more towards momentum flux. The main difference between momentum flux and the modified Briggs equation is going to be the terrain categories. So where these fans are going to be located, are they going to be in the middle of nowhere, or are they going to be in a big city? All have a direct effect on, your plume height. Why I'm showing you this is because, again, these are life safety applications. We want to make sure that we are being as accurate as humanly possible, when selecting these systems. So there are still some manufacturers out there that will use the modified Briggs equation to calculate their plume height. The reason for that is because using modified Briggs typically gets you a higher plume height. Okay. It's not a significant difference, but enough that, it'll make you turn your head and be like, wow, okay, this competitor can get this much higher of a plume height than Greenheck. And it's just something that we want to make people aware of, because at the end of the day, it's not what we want to see be used, just because it's not nearly as accurate. We default to the momentum flux equation in our selection program, but we keep the modified Briggs I should say, on deck in our selection program, just because when we get that inquiry that comes in that says, hey, how come, this manufacturer has a 10-foot higher plume height, a higher 10-foot plume height than you, we want to be able to explain to them, hey, they are using the modified Briggs equation. So what we simply do is, once we get that call, we simply switch our selection from momentum flux to modified Briggs, and we're usually dead on the money with our competitors' plume height. Okay, so at the end of the day, it's a sales tactic. Okay, people want to claim that their fans can do better than their competitors' fans, but I'm here to tell you, and I'm sure you guys know, these fans, it's not rocket science. Okay, if you have the same fan, same wheel, same motor, it doesn't really matter who you're going against, you should have relatively close to the same plume height. All right, so moving on here now, we'll talk a little bit about the older lab design. It used to be you would have, one hood, one fan, okay? That used to kind of be how the industry was laid out. Nowadays, we are at the manifold exhaust system, where you're going to have multiple hoods going up into some kind of common ductwork, and then up into one or two fans, compared to, if you have one fan per one hood, you may have 20 different fans on that roof, which in return requires a lot of maintenance, a lot of upkeep, and it's just simply not as efficient. So what we do now is we move to this manifold exhaust system. Again, all these hoods going up into some kind of common ductwork. And then with that, we kept a couple hoods off here to the side. As you can see, why we did that is just to remind everybody, not all exhausts are compatible with each other. Obviously, we want everyone to do their homework on what exhausts can be mixed, with each other. So, there still may be times where you're going to have, 10 to 15 hoods going up into, maybe 2 or 3 fans, but you're still, you might have that requirement of having 1 or 2 smaller fans off here to the side, just because you are not able to mix the exhaust. All right, so moving on here now, we are going to be talking a little bit just about pre-engineered versus built-up systems. Earlier in the presentation, we talked about that, these systems can get, slightly expensive, especially, when you go to the larger systems. We understand that, every different job is unique. We understand that, different aspects of the fans may need to be changed in order to meet spec. What we are trying to push in the industry is we want to stick with the pre-engineered system as best as we possibly can. So you're going to notice this built-up system here. It is a lower purchase price up front, okay, but a much higher install cost. And the biggest thing is going to be, we don't know how this fan is going to perform out in the field, just because if you're adding different bits and pieces from third parties to that system, we truly, it's never been tested. So we simply don't know how that fan's going to perform. And in the long run, it could cause you a lot of headaches down the road. With that, you're going to notice that this system, for the built-up system, is much smaller compared to this pre-engineered system here down in the right-hand corner. But even though this system is much smaller, you're going to notice the guy wires on this, okay? Reason why there's guy wires is because they are using a third-party curb, as you can see, so a curb not from the manufacturer. All of our laboratory exhaust fans come with 125-mile-an-hour wind load ratings without guy wires, okay? That standard remains if you use our curb. If you do not use our curb, that is when guy wires will need to become required, just because, again, we don't know how stable that fan is truly going to be out in the field sitting on a third-party curb, just because we've never tested it. Moving down here now to the pre-engineered systems. So the pre-engineered systems, Yes, it is a little bit higher purchase price up front, but lower install costs. And the biggest thing is going to be all of this system was tested at our factory. So you know how this system's going to perform once it actually gets out in the field. There's not going to be any surprises, bearing any problems. But again, it relieves the headaches down the road. There's far less problems with that. And you're going to notice how big this system is compared to this built-up system. This pre-engineered system is extremely large, and yet there's no guy wires in sight. Okay, everyone wants to avoid guy wires. That's kind of the common trend where the industry is going, just because they are more of a hassle than anything. And sticking with that pre-engineered system usually eliminates the need for guy wires. That being said, when talking about guy wires, if you're going to be adding a decent amount of stack extensions or whatever it may be, you obviously, as the system gets taller, then at a certain point, guy wires will need to become required, just because, if you have a 30-foot high system, that it needs some extra support. Okay, so moving on here now, we have our 3 control loops that remain constant in every single laboratory space. First control loop is going to be your face velocity or your hood velocity. So the air moving over those hoods, typically that's going to be around 80 to 100 feet per minute. You usually don't see anything much faster than that, just because if you go over 100 feet per minute, that is when you run the risk of ruining, whatever you're working on inside of this hood. So that's control loop number 1. Control loop number 2 is going to be how you pressurize your space. So the air coming back down into this space, typically that's going to be a negatively pressurized space. You will run into different situations as far as, OR suites, maybe different types of isolation rooms that will be positively pressurized, but typically it's going to be a negatively pressurized room. Control loop number 3 is going to be your duct static, but that is controlled by your bypass air plenum. So let's say the demand from the space below decreases. So let's say, your hoods, start to shut down for the night. As they shut down, your duct static changes. As that changes, in order to relieve some of that duct static pressure, we need to modulate our bypass air plenum open. Okay. And on top of that as well, modulating that bypass air plenum open, or bypass air damper, excuse me, will allow us to maintain our targeted outlet velocity and targeted plume height. So just to sum up one more time, the 3 control loops, again, your face velocity or hood velocity, 80 to 100 feet per minute. Your lab pressurization, so how you pressurize your space below here, typically, again, negatively pressurized space. And then your duct static, which can be relieved through the bypass air damper. All right, so now we are actually going to start diving into the nuts and bolts of your typical laboratory exhaust products that you will see out in the field. We're going to start on the small side. So this is what we call our Vektor H. So one of our high plume offerings. This is one of the smaller fans that we can offer in the laboratory market. These fans are capable of doing right around 24,000 CFM up to about 4 inches of pressure. Okay, so they are built for smaller jobs. Again, still 125-mile-an-hour wind load rating without guy wires, and then we can offer belt or direct drive construction. The direct drive construction here is going to be this image off to the right. That is actually fairly new to the industry when it comes to these small of laboratory fans. And this actually really sets Greenheck apart in a lot of different ways from the industry, just because a lot of competitors cannot offer this small of an inline high plume laboratory exhaust fan in a direct drive assembly. We call this a plug and play type of fan. Very easy to set up, very easy to maintain, virtually no maintenance. you're going to notice this motor is actually kind of floating out here outside of the fan. Sometimes people ask, is that just for, a visual or a representation of, what you guys can do, or are you just trying to show the inside of the fan? But what we wanted to showcase is this is what we call our power pack. So the power pack actually, you see that where the motor sits, and then that wheel is actually directly below that motor. So if you ever need to get into this fan for whatever reason, you are very easily able to pop off this panel on the outside here. And as you pop that off and pull it out, the motor and the wheel all come out together. So it's a very simple design. That motor actually still sits in a housing right on the other side of this panel, which my apologies, you can't really see that housing too well. But that motor is isolated from the airstream. So, that you don't have to worry about that motor coming in contact with whatever's being exhausted out of there. That's another common question we get a lot, especially looking at these direct drive fans. A lot of people think that motor is within the airstream, and technically they're not wrong, but it's just not coming in contact with the airstream. So some of the applications that you will see these smaller high plume fans on is going to be high school science labs, college science labs, any job that doesn't require, high CFM capabilities or high pressure capabilities is a great application for these fans. What I want to point out is this last one at the bottom. So people think laboratory exhaust fans, they think laboratories, right? I work at a fan manufacturer, and that's what, I still think that. We are trying to change that narrative in the industry, which we will get into a little bit later in this presentation. But these fans can be used for different applications besides laboratory exhaust. One of them is going to be restaurant exhaust. You can get these fans with a grease exhaust rating. As you can see here, this image off to the right, that is our fan with a grease exhaust rating. The main difference between this fan and then your typical laboratory fan is going to be, vented roof curves to prevent heat buildup. And there's going to be a cleanout located in the lower plenum box where, obviously you can clean out all the grease and, keep that fan well maintained. Sometimes people ask, they say, why would you want to put a laboratory fan on a restaurant? What I always tell people is, if you live in a big city and you live next to your favorite burger joint, steakhouse, whatever it may be, that's going to smell good for a couple of hours, but you're not going to want to smell it every single day of your life. That is where these fans come in. Okay, so we have that offering. We are able, we do see it every now and then. It's not a huge demand by any means, but we do want to let people know that we are able to offer it, and that is an option to them, if the opportunity ever arises. Moving on here now. So now we'll talk about the more typical laboratory exhaust fan that you see in the industry. It's going to be the mixed flow, high plume dilution blower type fan. So these are the fans that, people associate laboratories with the most, I would say. Definitely built for bigger jobs, so capable of doing right around 80,000 CFM up to about 8 inches of pressure. Still 125 mile an hour wind load rating without guy wires. Spark C and Spark B options when it comes to these types of fans. We cannot offer Spark A on our laboratory fans, but Spark C and Spark B can come as standard, easily selectable in our selection program. You have your belt or direct drive arrangements, which we'll get into here in a little bit. Let's talk about the key design features of these fans. So you're going to see where this motor sits here. This is our direct drive arrangement. A lot of people think that motor sits within the airstream. It does not. That motor actually sits within a bifurcated housing where the air actually moves. It'll be up and around that motor. So this stack is a double wall housing stack where that exhaust is free to go up and around that motor and then into the nozzle and then into the atmosphere. So reason behind that is because, one, earlier we talked about NFPA 45. That's kind of a safety standard throughout the industry. Well, this is a safety design point, okay? If you ever need to get at this motor for whatever reason, work on it, replace it, we don't want you coming in contact with whatever's being exhausted, okay? So having this motor completely out of the airstream allows us to know that whoever's working on these fans is going to be 100% safe. Moving on here now, looking at our mixed flow offering. So one thing that kind of sets us apart a little bit from the rest of our competitors is going to be where our isolation dampers sit. So our isolation dampers actually sit above our bypass plenum. Why that is so important is because a lot of other fan manufacturers will have the isolation damper actually within the plenum. So if you need to get at that isolation damper, and if you're with one of our or if you're with one of the other manufacturers in the industry, you actually have to crawl into a contaminated area in order to take that isolation damper out, whether that's washing it, replacing it, whatever it may be. But for our particular design, this isolation damper sits on a track. You're going to notice this bolt hole pattern here on the outside. You simply unbolt and you are easily able to pull that isolation damper out, maintain it, check on it, make sure there's no leaks, and make sure everything's good to go. Moving on here now, another key design point when it comes to these mixed flow fans, or mixed flow plenums, I should say, is going to be our removable panels. So we understand that when that first inquiry comes in to us, or that first question comes in to when these fans are actually installed in the field, a lot of different things change. Okay, from point A to the installation date. One thing that changes the most is going to be where that inlet goes. Okay, so if you need to change your inlet in the field for whatever reason, you simply pop off one of these removable side panels, hook up your ductwork, and you're good to go. So it's a really, really nice design point. We want to make it as easy as we possibly can for you out in the field, or for your customers out in the field, just in case something changes in the design stage. So you're going to see the belt drive option here that we were talking about, and then the direct drive. This image actually showcases a little bit better where that motor is located and how that motor sits within that bifurcated housing. So that air will move up and around that motor, and then again up into the nozzle and then into the atmosphere. So completely isolated out of the airstream. Moving on here now, so just talking about, a couple of advantages to belt or direct drive. So the belt drive option sits in that box here on the outside. Much easier to service, much easier to get at, but because it is belt drive, more maintenance is required. Direct drive, there's less maintenance. Most fans come with 1-year lube intervals, but when maintenance is required, because where that motor sits, it is a slight project to get at that motor. So it's kind of a trade-off. Obviously, there are jobs that require direct drive, and there are jobs that require belt drive. But then there's those jobs that could go one way or the other. And we have reps that have customers that want belt drive because of the service aspect to it, and then we have reps that want direct drive because there's less maintenance to begin with. Okay, so it's kind of sometimes comes down to preference. And as I said, though, obviously there are jobs that require direct, and there are jobs that require belt. But nonetheless, two options that are at your disposal. Here are a couple of configurations that your typical configurations that you will see in the field, from 1x1 to 6x1 to 2x2 to 2x3, whatever it may be. Most manufacturers, including Greenheck, are able to accommodate to basically whatever you guys would need. But this is typically, your typical configurations. Moving on here now, so this is going to be the high plume offering. The only difference between the high plume and then what we were talking about before is just going to be the nozzle type. So the high plume, capable of doing right around 60,000 CFM, up to about 8 inches. Still built for bigger jobs. The main difference is just going to be this type of nozzle. This type of nozzle, nothing too crazy about it. You're taking a large space, condensing it down into a small space to create that velocity, and then to expel that effluent or contaminant out into the atmosphere. Excuse me. So talking about some of the pros and cons of the inline fans, you're going to notice one of our reps customers here standing next to one of our mixed flow units here. So the pros, smaller footprint on the roof deck. So you can have, pretty large systems on these roofs without actually, taking up a lot of roof space. Obviously, roof space sometimes comes at a premium just because of all the other systems up there, which is where, these mixed flow fans truly come into play. The cons, there's going to be a taller finish. So you're going to notice this guy standing next to this system here. Obviously a very large system, but it's going to take some effort to maintain these, to get up there, to check the motor, check the belts, whatever it may be. But the biggest thing, what people like about them is, they're large systems, but yet, the roof space is minimal. Or I should say that the roof space needed is minimal. Okay, so here we go. Now with the centrifugal high plume dilution blower. So this is going to be one of the fans that we like to push most in the industry. They are built for bigger jobs, so they're capable of doing right around 140,000 CFM up to about 14 inches of pressure. I've never seen a laboratory job that big yet. I'm not saying there's not one out there. Sometimes people ask, why do you have a laboratory fan that can, handle that much CFM and up to that much pressure? What we always tell people is, we want to be able to accommodate to whatever our refs customers need. Okay, no matter how big that job is, this fan usually keeps us in the game, or at least in the talks, when deciding which way to go. But they are built for bigger jobs. When looking at these fans, they are slightly more efficient. They have higher pressure capabilities. And one of the biggest aspects to these fans is going to be the service component to these. So that motor sits right at roof deck level here. Really, really easy to get at, really easy to maintain. You don't have to crawl up onto anything. You don't have to, struggle to get at a motor. You simply remove this panel here on the outside to get at the motor and to maintain it or do whatever you need to do. And it's a really, really nice feature. One of the cons when it comes to these systems is going to be the large footprint. Okay, so these fans, they're large systems. That's the nature of them, and sometimes they're just simply not in the cards. Okay, for you guys to be able to select, or if you guys are actually able to purchase, just because there are a lot of different other systems up on the roof, and sometimes there's just simply not enough room. We're looking at the configurations. This really showcases the footprint. When you go from 1x1 to 4x1, obviously that footprint gets much, much larger. And again, sometimes you simply can't do it, which is where you'd want to go to the mixed flow fans. But when roof space is there, this is where we usually like to start, just because the efficiency and the service component of these fans. Okay, so now, I understand, obviously, there's a lot of information throughout this presentation. If you guys remembered nothing else throughout this presentation, please remember this, take a screenshot of this or do whatever you want to do or take notes on this. We are trying to change the narrative in the industry that people always say you have to have a dilution nozzle when it comes to laboratory exhaust fans. And sometimes on certain jobs, yes, the dilution nozzle is required. But what we are trying to tell people and let people at least make them aware of that there is no code in this industry saying you must have dilution. Okay, we selected a fan at 30,000 CFM up to about 5 inches of pressure. The dilution came back. We're going to start with the brake horsepower here. Because you are entraining more outside air, so you're moving more air through that system, your brake horsepower does go up. So in this particular case, the brake horsepower was at 55.1 compared to the high plume offering, which was at 43.0. That is a significant difference, okay? And let me remind you, or let me just say that we're not showing this slide to discredit the dilution nozzle whatsoever. It is definitely still a key add-on or option in this industry. But we're just telling you, do your homework. Do you truly need the dilution nozzle, or can you go with a more efficient option and look at the high plume offering? A common, I should say, myth when it comes to these dilution nozzles is people think you'll get a higher effective plume rise with the dilution nozzle. But in this particular case, at 30,000 CFM at 5 inches of pressure, that is not the case. The dilution nozzle had an effective plume rise of 50.4. in the high plume had a effective plume rise of 54.0. So, not a huge difference, but nonetheless, again, the high plume still performed a little bit better when it came to plume height on there. And then the last one is going to be the relative cost on here. So obviously, with the dilution nozzle, it's gonna, require a little bit more brake horsepower, as we talked about, just because you are moving more air compared to the high plume, where you're not entraining any outside air, so that your brake horsepower or your power consumption can go down a little bit. Again, the dilution nozzle still a great, add-on or feature when it comes to these laboratory fans, but we just want to remind people that there is no code in this industry saying you must have dilution. A lot of people think you have to have dilution. That's because a lot of manufacturers out there say you have to have dilution because, that's pretty much the only thing they can offer on the laboratory fans. The important thing for you to remember is just to know that, there are other options out there. We're not going to push you to go one way or the other. That's Chris's job, obviously, but our job is just to let you know, do your homework, ask questions, and figure out what the best type of nozzle is for you and your application. So the typical, mixed flow, centrifugal applications, larger jobs, university labs, pharmaceutical companies, any job that requires, higher CFM capabilities or higher pressure capabilities is where you're going to see these types of fans. Moving on now. So an option that not too many people know about is going to be a rooftop assembly option. So this is where, you have your laboratory exhaust fans, let's say in like a mechanical room or whatever it may be, and then you would actually duct up to the roof, and then you would have a stack and a nozzle on top of that roof. Why I'm showing you this again is just to let you know that, hey, if you ever run into a situation where, if you're working on a job that maybe requires the fan to be inside a building, that just know that you do have an option. Know that, we can accommodate to that, as can many other manufacturers out there. What I always tell people with these rooftop assemblies, or at least to be cautious on, is, these fans are in the building. So depending on what they're exhausting, it's extremely important that people are constantly checking up on these fans, because if there's a leak of some sort or whatever it may be, within the space below, that exhaust is, simply going back into, where people are. Okay. So we want to make sure that there is no leakage. We want to make sure that these fans are well maintained. But again, this is an option for you. These stacks up top are actually a curb mounted stack. They come with 125-mile-an-hour wind load ratings, again, without guide wires. Usually 10-foot minimal is what we like to see, and it goes back to NFPA 45, where no one can stick their hand or their face or whatever else over whatever's coming out of these fans. So now talking a little bit about sequencing these fans, it's another common question we get a lot. We're just going to go through a couple of common practices, what we usually like to recommend when turning these fans back online and when turning the fan off. So we're going to start with the system. Both fans are doing 5,000 CFM, 10,000 total. Right now, the space below is giving off 7,500 CFM. We are modulating our bypass dampers open to 2,500 CFM. As we move on, the CFM below the space, again, is going to keep decreasing here a little bit. So now we are at 5,000 CFM and now 5,000 of additional bypass air. Both fans, both taking on half of that load of that 10,000 CFM. Now, as that demand or that CFM from that space decreases enough, we are able to actually shut a fan off. The best way to shut a fan off, it says fan and isolation dampers should be powered off at the same time. Or what I like to recommend, what my boss likes to recommend, is shut the isolation damper first, then shut the fan off. Why we want to shut the isolation damper off first is simply because if you shut the fan off first, and then shut your isolation damper completely closed. As this fan is ramping down, there is still some kind of negative pressure in this space down here. So you run the risk of pulling air back down through this system if that isolation damper is not fully shut yet, and then spinning this fan backwards. And as I'm sure most of you know, that could cause a lot of headaches out in the field. So we want to make sure that that isolation damper is shut first, and then we can start ramping our fans down. Same thing with sequencing the fans back online. We want to start that fan up first and then modulate or I should say open our isolation damper, just because it eliminates the risk of any potential air being pulled back down through this system and then spinning that fan backwards. So moving on here now, I apologize. I am kind of moving a little bit fast here. We're getting a little bit close to our time. So we're going to start talking about our accessories on these fans. A couple things that we can offer, other manufacturers can offer. And, sometimes we just want to make people know that, hey, you need this or you don't need this. And we just want to make you guys as efficient as possible. So starting with the standard bypass plenum, right? Nothing too special about it. One of the more common options, obviously, in the industry, usually on every single laboratory fan, depending on the application. Obviously, there are jobs that don't require any plenums, but single wall construction, again, nothing too crazy about it. The biggest thing with these bypass plenums that we want to remind people is we do not want to exceed the maximum velocity of 1,500 feet per minute with that air entering the plenum. Why we don't want to exceed 1,500 feet per minute of that air entering the plenum is because anything faster than that, we have run tests where turbulence is then created in here. If it's coming in, I'd say at 2,000 feet per minute, and as turbulence is created in here, that can have a direct effect on your fan performance. The next option that you see every now and again is the double wall bypass plenum. So this is used to insulate exhaust airstream to prevent condensation. That is mainly the goal of these double wall bypass plenums. A couple things to keep in mind when adding this type of plenum, you're adding a decent amount of weight to that roof deck. And most of the time, from what we have seen, from manufacturers, when adding these double wall bypass plenums, your lead time greatly increases. Obviously, lead time is a huge topic of conversation. Doesn't really matter who you're going with, either it's through us or any of our competitors. Everyone wants to have the fastest lead time. So what we always tell people with this double wall bypass plenum, if it is, required, we always say at least question it. Is it truly required, or can you get away with your standard bypass plenum? But nonetheless, just to let you guys know, it is an option. It is at your disposal if need be. Moving on now. So these fans, these laboratory exhaust fans, they are loud. That's the nature of them. They're moving high amounts of CFM at usually higher pressures. We need to come up with ways to combat some of this sound. One of the ways to combat some of this sound is through attenuated wind band and wrap. So basically, it's just a different type of nozzle that reduces the outlet sound of these fans. The other option is to go with the inline discharge attenuator. Again, used to reduce outlet sound. One thing with the inline discharge attenuator, when adding this to a system, you are adding height to a system. Okay, so when adding height, making that system taller, there is the possibility that guy wires will need to become required. Whereas if you go with the attenuated wind band and wrap, guy wires are not going to become required just because you're not adding height to the system. Where I like to start when it comes to combating sound is going to be through the inline bypass attenuator. Okay, depending on how much additional bypass air you are pulling in through that system, this can be one of the noisier parts of the fan. Okay, these bypass dampers are sized a little bit smaller, and they're sized a little bit smaller on purpose in order to create velocity, create velocity going through the system. So while creating that velocity, and if you are pulling in high amounts of additional bypass air, that part of the fan can really, really hum. Okay, so I mean, it can get pretty noisy where, you know, if you add this bypass attenuation, you're not adding any height to the system right at roof deck level. And on top of that as well, again, depending on how much additional bypass air you are pulling in, you're combating one of the louder parts of the fan. Another common option that is out there in the industry is going to be the crane assembly option. Just basically provides means to remove motors and wind bands in elevated assemblies. With this option, it basically takes, you know, the responsibility out of someone else's hands, puts it back into your hands where, you know, you don't have to wait on someone to come out there with the crane in order to lift bits and pieces of this fan off. You know, and it's just essentially, you know, speeds up the process of whatever you're trying to do on this fan, or if you're trying to assemble this fan or whatever it may be. And again, it doesn't make you wait on someone. One thing with this crane assembly is you're going to notice where these posts are down here, there are sockets lined up, or I should say in or bolted into this plenum here. What we always tell people is if you are unsure if you need a jib crane assembly, we always tell you to at least add these sockets up front. If you don't add these sockets up front, you are not going to be able to add that jib crane later in the field. Reason behind that is going to be because these jib cranes are extremely heavy. And on top of that, they're lifting some pretty heavy material off of these fans. So if these sockets are not properly installed, it becomes a safety factor where, you know, if something would happen, if one of these sockets would let loose or whatever it may be, you know, there is the possibility of someone getting hurt up on the roof, which is obviously not something any manufacturer wants, including Greenheck. So what we always tell you guys is just let us install these sockets in our factory. And then if you want to add the jib crane later in the field, you are free to do so. Okay, so moving on here now, going to an option that is definitely becoming more prevalent in this industry. I'm not going to spend too much time on this unless people have questions on it. Just to let you know that, hey, you know, we can offer it and some of the best practices that we use. So as we talked about, laboratories are energy hogs. You know, that's the nature of them. When I first started at Greenheck, I actually, one of my great mentors, he was one of the backbones of creating the laboratory exhaust line here at Greenheck. And he always told me, you know, back in the day, when creating this laboratory exhaust line, energy consumption was on the bottom of the priority list. Obviously, nowadays, energy consumption is on the top of the priority list. Okay, so having energy, some kind of energy recovery can sometimes, you know, help out your bottom line and just overall help your efficiency. I'm going to skip this slide. So what we don't want to see in energy recovery systems is we don't want to see any wheels or plates be used, just because there is that possibility of exhaust, you know, the cross-contamination aspect of it. Whereas if you use runaround coils, supply and exhaust ducts are not brought together, so there's no possibility of cross-contamination. That's what we use. Most manufacturers use that, but every now and then you will hear about some type of energy recovery that is using a wheel. This is just a nice pictorial of a typical energy recovery system. So again, your runaround coils is what we use. So our coils are all dipped in, we call it E-coat. It's a little bit better, I should say about equal to the heterosite coating that is the most common in the industry. So our E-coat is what we use on our coils. We manufacture our own coils, which is also really nice. So we have the ability to modify them a little bit if need be. Just to sum up, again, wheels, plates, not recommended, as I'm sure all of you guys know, and the runaround coil loops is usually what we want to see. So as we talked about before, I said later in the presentation, you know, we're going to come back to, or I talked about restaurant exhaust before on our smaller inline high plume fan. You know, we want to change the narrative that these laboratory exhaust fans are not just for labs anymore. They can be used on other different applications. a couple of them, being ammonia exhaust, wastewater treatment, diesel generator exhaust. And again, the whole point of showing you this is we just want to make sure that you guys are aware that, hey, just because it's not a laboratory doesn't mean we can't use a laboratory fan. Starting off with the diesel generator exhaust. So actually before Greenheck, I was an account manager for a generator company. My job was to work with these big generator assemblies. When these generators turn on, obviously that exhaust needs to go somewhere. So we have created an option where you can use one of our Vektor fans or one of our laboratory exhaust fans in order to expel the diesel generator exhaust. And again, without any possibility of re-entrainment into makeup air systems or coming in contact with the general public. Wastewater treatment. So this is going to be a great example
Hey,
of
Justin.
Yes.
Before we move along, we got a question in the chat from Mary. It's actually about, I think, something you kind of touched on earlier in the presentation.
Sure.
Mary wants to know maybe if you have any more information or guidance on the kinds of adjustments to discharge velocity and stack height that a designer might incorporate when there's, like adjacent buildings or screen walls or just other things.
Great
Physical
question.
obstructions going on at the discharge of the fan.
Great question, and thank you for that question. I appreciate it. So let me see if I can. This will work. So let's say these arrows right here. Let's say these are skyscrapers or another building or whatever it may be next to this fan. And what we usually like to do, if there are buildings next to our fans, we will add some type of stack extension onto this system, so to make that system much taller in order to expel that exhaust up and over those buildings. And again, depending on how tall those buildings are, we might need a significant amount of stack extension. One thing with stack extension, so we talked about guy wires before. Obviously, when adding stack height, guy wire is going to become required, but to kind of touch a little bit more on your question, when when tall buildings are next to these fans, a significant amount of stack extension may be required. So when that is required, we will add some kind of, or not us, but you or whoever's in charge of that space will add some kind of scaffolding around these fans and then hook that up to some kind of solid structure in order to make sure that fan is 100% stable. But I understand I kind of went on a rant there of what we typically do or what we usually recommend. But bottom line is stack extensions, making these systems taller. Or on top of that, we can look at higher outlet velocities as well, which is something that we are able to adjust in our selection program. But both options are usually generally what we like to recommend when going into or when increasing your outlet velocity in order to achieve a higher plume height. One thing to keep in mind is when increasing that outlet velocity, because you are increasing that, what do you think happens to your brake horsepower? It goes up, right? So, larger motors then are required, which is sometimes not something people want to deal with. But then the other option would be, simply just adding stack extension in order to achieve, a safe, effective plume rise.
So doing those modifications, trying to decide when we would want to do that. You're saying that the plume height, the plume rise,
yep,
is we want to get that above any of the neighboring obstructions.
Correct. Yep. So that's the main goal. So let's say, this fan, for example, let's say we have a building, right. I don't know if you guys can you guys see my mouse or not?
Yeah, we can see your cursor.
Okay, perfect. So let's say there's a building, somewhere downstream right here. The whole goal would be to get that plume up in a way far enough where by time, let's say, it does come in contact with this building, it's diluted enough before it actually comes in contact with, say, other systems on the roof or a general public on there. Which in return, obviously, again, coming into those stack extensions, if you need to get that plume height up higher, that's a great way to dilute that exhaust a little bit more in order to essentially eliminate any possibility of it coming in contact with neighboring buildings.
Got it. Thanks, Justin.
And Justin, correct me if I'm wrong, inside caps, we actually do have a concentration kind of plume rise.
We do.
That will generate in our selections. So if you're worried about how close you are to a neighboring building, at what height, it'll give kind of a visualization of what the concentration level would be as the wind takes it in that direction, maybe towards an adjacent building that you're concerned with. So that's a really cool feature that was added into caps within the last year or so, I believe.
Yep. And if you don't mind, I actually have that example in this presentation. I hid that slide just because sometimes it takes up a lot of time and we only had an hour. But if you don't mind, I could definitely go back to that right now and showcase that. It'll be, unless you guys don't want me to, that's okay too.
I think maybe Chris might be trying to say that we're running a little short on time.
Yeah, so we're running short on time. So if people have to run and jump to another meeting, thank you for joining us. Feel free to reach out to us anytime. We're going to let Justin continue on here. And so I want to see that slide. I think it's a really useful one and talk about a few other things. But for those of you who have to get running, thanks. And please reach out to us. We're happy to give this presentation to anyone who needs it. All right, Justin, keep going.
Thank you, Chris. Yeah, and thank you everyone who attended. Definitely much appreciated. Our apologies, we only had an hour here, but thanks for taking time out of your day to listen to me talk for a while. So again, wastewater treatment. Again, this is where you'd want to use the dilution nozzle. Wastewater treatments usually have a pretty nasty smell to them, so using the dilution nozzle can help dilute some of that smell before it actually gets into the atmosphere. And I'm going to kind of fly through this a little bit, but emergency ammonia exhaust systems as well. We see that's a very common, I should say, application for our Vektor fans. For those of you who don't know what emergency ammonia exhaust systems are, basically any building that has a large refrigeration system, such as ice rinks. I would say NHL hockey rinks are the biggest contributor to this, is where you need some type of emergency ammonia exhaust system. Couple of different things about it, Spark B construction only. That's all we offer when it comes to emergency ammonia exhaust system. And the discharge needs to be 20 feet outside of property lines as well, because that ammonia is extremely hazardous to the general public. So we want to make sure that there's absolutely no possibility anyone's coming in contact with that. So here's the virtual lab demo, but I think I'm going to do for Mary's question, and I don't know, is Mary still on? Not sure if she is. But one thing I'm going to show here to what Mary was talking about and what Chris was talking about is going to be so our Chris was talking about the tool that we have in CAFs as far as being able to determine how diluted exhaust truly will be at some point downstream. So this is what we can showcase. So let's say, there was neighboring buildings somewhere downstream here. This is where that little dot is going to be. So let's say this is a building. You are able to tell based off our selection program, just how concentrated that exhaust will be at a certain height. Okay, so if it's going to be safe or not for a neighboring building. You're going to know when to, if you need to increase that plume height a little bit by either stack extensions or increasing your discharge velocity. And as Chris said, this is a really, really nice tool. Kind of puts people at ease as far as, if you have jobs in big cities. This allows you, to showcase how diluted an exhaust or whatever an effluent or contaminant will be at a certain point downstream. So I really appreciate that question if you're still on. But other than that, because we are over time already, I'm going to stop there. I do not have anything else unless people have other questions.
We'll hang around a bit, see if anybody puts a question in the chat. But to everybody, thanks for joining us, and we'll see you again next week on Wednesday for the next Power Hour presentation. And thank you, Justin.
Absolutely. Thank you guys. I'll hang around for a while here.
Yeah, to anyone else interested, we give a very similar presentation, the Dorsey sales engineers. We have access to Justin's virtual lab demo where we can go over you got a fume hood applications and variable volume, different nozzle types, different fan types, and comparisons. So if you're interested, we're happy to come in, whether in person or virtual, and give those presentations.
Yep, absolutely. And for those of you still on, this is the virtual lab demo. Hopefully everyone can see my screen. Can you see my screen, Chris?
Yep.
Perfect, perfect. So yeah, to Chris's point, they have access to this as well. This is our virtual lab. Great presentation tool. A little bit more interactive than just a PowerPoint. Sometimes it arises, makes people ask a little bit more questions compared to, just your standard PowerPoint. But they have access to that. They have access to the presentation I just gave as well. So please, if you need anything, I mean, you guys are in great hands having Chris there and his team.
Looks great. Thanks a lot, Justin. And thanks everybody for joining us.